Any questions about anything we've been doing about groups, subgroups, normal subgroups, homework problems? So suppose we have two groups, G1 and G2 be groups. We can define the product group G1 cross G2. This is all, let's say, ordered pairs, x1, y, x1, x2, where x1 is in G1 and x2 is in G2. And we can multiply ordered pairs coordinate-wise. So what this means is, if you have the pair x1, x2 times y1, y2, that's the ordered pair x1, y1, comma, x2, y2. And if G1 and G2 are additive groups, then we write the binary operation additively. We have x1, x2 plus y1, y2 is x1 plus y1, x2 plus y2. And this is something, of course, you're very familiar with, because if we take G1 and G2 to be the additive group of real numbers, R cross R is just a set of all pairs of points x1, x2, where x1, x2 are real numbers. You're just looking at the plane. R cross R, or we sometimes write this as R2. And this is just vector addition. So example, vector addition in the plane. So the idea of the product of two groups is really something that you've seen. Yes? Is there a question? Question? And you can take the product of any two groups. So example 2, right? This was example 1. R2. Take your two take your two favorite groups. So for example, suppose we take G1 to be S3 and G2 to be the group just consisting of the numbers 1 and minus 1. So this is the symmetric group. The order of S3 is 3 factorial, or 6. the order of this group G2 is just 2. It's just the numbers plus and minus 1 with multiplication. So G1 cross G2, this is all ordered pairs, sigma 1 for all sigma in S3, together with all ordered pairs sigma minus 1 sigma in S3. All right? This is all possible choices of a permutation for the first coordinate and the number 1 or minus 1 for the second coordinate. And you can see, for example, the order of G1 cross G2. Well, this is for any groups. It's just the order of G1 times the order of G2. Because when you're looking at the coordinates x1, x2, you have this many choices, order of G1 choices for the first coordinate, and you have order of G2 choices for the second coordinate. So if we look at the product S3 cross, let me just call this gamma 2. Gamma 2, the order of that is 6 times 2, or 12. So this is a group of order 12. Okay. So it would be nice to know, in some sense, what are all the groups? And that's a hard problem. There's a lot of groups. And the difficulty is that when you have any two groups, you can build a new group just by taking the product. And you can iterate that. You can take the product of the product of the product and so forth. So there are lots of ways to build up groups by multiplying groups. The really important new way to understand groups is by dividing one group by another. This notion of what is called the quotient group. So let G be a group, let N be a normal subgroup of G. So what does normal mean? Let's just recall the definition. N is normal, the subgroup N is a normal subgroup if every left coset equals the corresponding right coset for all x in the group. And we prove that this is equivalent to saying the following. If we take the subgroup N, multiply it on the left by x and on the right by x inverse, this is always contained in N for all x in G. So these are equivalent statements, but to prove that takes just a couple of lines, but it does need a proof. And it's important to know that these two statements are in fact equivalent. So whenever you have a subgroup, we look at G mod N. This is the set of left cosets of N. That means the set of all xn for x in G. But of course, if this is a normal subgroup, every left coset is a right coset. So this is the same as the set of right cosets of N, or the set of all n times x, x multiplying n on the right, x in G. And I want to define multiplication of cosets. That is, if you have a coset xn and you have a coset yn, I want to say this is equal to some coset zn, where z depends on x and y. So we want to define in a coherent, non-contradictory way the product of two cosets. And an obvious choice, so obvious choice to at least try, is z just equal to x times y. And we're going to show that, in fact, this works. This makes sense. So in order to show it makes sense, we have to show that this is well defined. So first of all, let's recall the product of two sets. So just the product of subsets A and B of a group is just the set of everything you can write as an element of A times an element of B for A and B and B. Right? So what is the product in this set theoretical sense of cosets xn and yn? So xn is the set of everything of the form x times a, where a is an element of n. That's the definition of a left coset. And yn is the set of everything of the form y times b, where b is an n. So if I take xn times yn, the product of these two sets, this is everything of the form x times a times y times b for all b and n. And now we use normality. We know that we know that the coset yn is equal to the coset ny. Right? That's what it means to be a normal subgroup. So the element a times y is in ny, because this is an element of n times y. But ny is equal to yn. So that means there exists some element c in n such that a times y is y times c. So if I take this element xayb, that's x times ay times b, but ay is y times c, so this is x times yc times b. So this is xy times bc. And of course, a, b, and c are in n, which is a subgroup. So b times c is certainly in n. So this is in the left coset xy times n. So every element of the product of the coset xn with the coset yn is in the coset xyn. Any element is in xyn. So we've just proven that xn times yn is contained in the coset xyn. But suppose I take something in xyn, that z be in xyn. So z is x times y times something in n for some b in n. And x times y times b is x times e times y times b. You can always multiply by the identity. E is in n. But now we see that z is in the left coset xn times the y times the left coset yn. This is something in the left coset xn. This is something in the left coset yn. So xyn is contained in xn times yn. So this is an important argument, and I'm going to repeat it. I'm just going to go through the whole thing again, because it is the crux of the construction of a quotient group, which is one of the central building blocks of group theory and algebra. So claim if n is a normal subgroup of G, then the left coset xn times the left coset yn is the left coset xyn for all x and y in the group. So let something, let's call it, I don't know, G, be in xyn. So what this means is that G is xy times b for some element of the group. That's the definition of a left coset. Therefore, G is also x times e times y times b, but you can always multiply by the identity. And this is xe times yb. Xe is in the left coset xn, yb is in the left coset yn. So G is in the product of these two cosets. So every element of xyn is contained in here. So the left coset xyn is contained in xn times yn. And now we have to prove the converse. Suppose that G is some element in the product of these two cosets. So then G is the product of something in xn, x times a, say, times something in yn, let's say y times b, for some elements a and b in n. So G has this form. But n a normal subgroup means that the left coset, the right coset ny equals the left coset yn. So a times y is in ny, because this is an element of n times y. So A times Y is in Yn, because these two sets are equal. They're the same set. So A times Y is YB for some element B in the subgroup. So therefore G, which is X, A, Y, B, AY can be written as YB, as YC for some C and N, YC times B, which is XY times CB. CB is an N because these are elements of the subgroup. Subgroup is closed under multiplication. This is in the left coset X, Y, N. So every element of Xn, Yn is contained in XYN. So therefore Xn times Yn is contained in XYN. And when you take these two statements in the red boxes, each set is contained in the other. So Xn times Yn is XYN. So this is one of the most complicated things to learn in beginning algebra, and you really need to spend a lot of time studying this construction. It's very important. And the point of all this is the following theorem. If G is a group with a normal subgroup N, the set of left cosets G mod N with multiplication defined by Xn times Yn is XYN is a group. And the name of this group is the quotient group. In some sense, it's like G divided by N. So proof, first of all, coset multiplication, as I just defined it, is a binary operation on G mod N. That is, the product of two cosets is a coset. Is it associative? Right? What are the properties of being a group? The multiplication is associative. There's an identity, and every element has an inverse. So if I take Xn times Yn and multiply it by Zn, what do I get? Xn Yn is Xyn times Zn. This is Xy times Z times N. But in the group, multiplication is associative. So Xy times Z is the same as X times YZ. And then we unpeel the onion. This is Xn times YZn, which is Xn times Yn times Zn. Done. Xn Yn times Zn is Xn times Yn times Zn. So this shows that multiplication of cosets is an associative group operation. What is the identity? If you take the left coset En, this is just E times A for all A in the subgroup N. E times A is just A for all A and N. That's just equal to N. So the left coset En is just the subgroup N. And if I take En times Xn, that's Ex times N, which is X times N. And similarly, Xn times En is Xe times N, or Xn. So the coset N, or En, is a left and a right identity. So this is the identity in the quotient group. And what about the inverse? Well, if I take the left coset Xn times the left coset X inverse N, that's X inverse N, which is En, which is N. And in the opposite direction, X inverse N times Xn is X inverse Xn, or En, or N. So therefore, the inverse of the coset Xn is the coset X inverse N. So every element has an inverse, and that's the end of the proof. We just proved that the set of cosets of a normal subgroup is a group. And recall the important fact that if G is abelian and H is any subgroup of G, then the left coset XH, which is everything of the form X times H, H and H, because the group's abelian, XH is the same as HX, which is the right coset HX. So every subgroup of an abelian group is abelian. So let's look at some examples. Let's take a finite cyclic group written additively. So let's suppose we take G to be Z mod 6Z. So this is congruence classes modulo 6. So this is an additive group, and it's abelian, right? The elements are everything of the form A plus 6Z. Right? Just these cosets. And let's, for example, take as a subgroup H to be 6Z, 2 plus 6Z, and 4 plus 6Z. So these are three congruence classes. And I could just denote them maybe more briefly as 0 bar, 2 bar, and 4 bar, where we write A plus 6Z sometimes as A bar just to have less to write. This is a subgroup. Right? What is the addition table? 0, 2, 4, 0, 2, 4. Your addition. You add 0 to anything, it doesn't change it. 2 plus 2 is 4. 2 plus 4 is 6, which is 0 mod 6. 4 plus 0 is 4. 4 plus 2 is 6, which is 0. 4 plus 4, which is 8, which is 2, which is 0. This is the addition table. For the subgroup H. That's a subgroup. Now, the order of G, which is the order of 6 mod, Z mod 6Z, what's the order of this group? Someone tell me? How many cosets are there? You can almost count them on your fingers. How many cosets are there? Here we have the set of 0, 1, 2, 3, 4, and 5. How many numbers are in this set?
6.
6, thank you. This group has order 6. How many elements or how many cosets or how many congruence classes are in the subgroup H?
3.
Thank you. So how many elements, how many left cosets are there? By Lagrange's theorem, this is the order of G over the order of H. That's 6 over 3, that's 2. So the quotient group is going to only have 2 elements. So what are the 2 elements? Okay. So we have G is the additive group of congruence classes mod 6, 0, 1, 2, 3, 4, and 5. H is the 3 congruence classes 0, 2, and 4. What are the left cosets of H? Well, we could have 0 plus H. Right? That's equal to 0 plus 0, 0 plus 2, 0 plus 4. That's just 0, 2, and 4. That's just H. So 0 plus H is H. What's 1 plus H? 1 plus 0, 1 plus 2, 1 plus 4. 1 plus 0 is 1, 1 plus 2 is 3, 1 plus 4 is 5. So this is also a left coset. And we know there are only 2 of them, so that's it. So G mod H consists of the left cosets, 0 plus H, which is H, and 1 plus H. So this quotient group consists of just 2 elements. Suppose we tried another coset. Suppose we took 3 plus H. That would be 3 plus 0, 3 plus 2, 3 plus 4. 3 plus 0 is 3. 3 plus 2 is 5. 3 plus 4 is the congruence class of 7, which is the same as 1. So the left coset 3 plus H is the same as the left coset 1 plus H. That's there, and so on. I mean, you can you can calculate all 6 cosets, and you see that there are only 2 different ones that appear. Each appears 3 times. And the quotient group contains 2 elements. So we have the order of G is 6. The order of the subgroup we looked at is 3, and the order of this group G mod H is 2. And 2 times 3 is 6. Let's look at another example. Suppose we take the group S3, and suppose we take H to be, suppose we take sigma to be the cycle 1, 2, 3, and let H equal sigma, which is E sigma and sigma squared. This is the cyclic subgroup generated by sigma. Why is this a group? So sigma is 1, 2, 3. What is sigma squared? When you multiply this by itself, 1 goes to 3, 3 goes to 2, 2 goes to 1. That's a different cycle. What is sigma cubed? 1 goes to 1, 2 goes to 2. Sigma cubed is the identity. So this set of 3 permutations, the identity sigma and sigma squared, that forms a subgroup. It's the group generated by taking all positive and negative powers of sigma, but of course sigma inverse is sigma squared. That's what it means to say sigma cubed is the identity. And we already did the exercise to show that H is a normal subgroup of S3. And you can check this very easily, because if you take E times H, or sigma times H, or sigma squared times H, or H times E, or H times sigma, or H times sigma squared, these left cosets and these right cosets, in fact, they're all the same. They all give you H. So sigma H is H sigma. And if you take any transposition, if you take, for example, the transposition 1, 2 times H, or if you take H times 1, 2, in both cases, what you get is the set of all 3 transpositions. These are the three transpositions in S3. And similarly for any of the other 2 transpositions, 1, 3, H and H, 1, 3, and 2, 3, H and H, 2, 3, they're all the same. They're all equal to this set. So H is a normal subgroup. Of G. And once again, the order of S3 is 6. The order of H is 3. So this quotient group, S3 mod H, is going to have 2 elements. And what are the 2 cosets? Well, you have H, the subgroup itself, and you have 1, 2H. So this consists of E, sigma, and sigma squared. And this consists of the three transpositions. And that's what the quotient group looks like. Questions about this? Again, this is really material that you need to spend a lot of time by yourself at home thinking about. Let's look at an example that you know from high school algebra or calculus. Suppose we take G to be R2, the XY plane. And suppose we label points X comma Y. So this is the set of all vectors XY, X in R, Y in R, with vector addition. X1, Y1 plus X2, Y2, the sum of two vectors is X1 plus X2, Y1 plus Y2. That's how you add points in the plane. Suppose I take H to be the set of all vectors where the Y coordinate is 0. What is that? That's the x-axis, right? The set of all points with the y coordinate 0 is the x-axis. And this is a subgroup. Because if you add x1 comma 0 and x2 comma 0, you get x1 plus x2, 0 plus 0, which is x1 plus x2 comma 0. So the sum of 2 points on the x-axis is on the x-axis. And R2 is abelian. It's an abelian group. So H is normal because every subgroup of an abelian group is normal. Now, what are the cosets of H? Let's look at an example. Suppose we consider the point, take a point on the y-axis, 0y. What is the coset 0y plus h? Maybe I'll call it 0b. What is the coset 0b plus h? This is everything of the form 0b plus x0 for all x0 and h. When I add these two vectors, I get the vector x comma b for all real numbers x. What is this? B is fixed. The set of points x comma b is this horizontal line going through the point 0b. So the x-axis is h, and this coset is this horizontal line. So every line parallel to the x-axis is a coset. Suppose I take some other point AB. Suppose I take A comma B plus H. So this is an arbitrary left coset. So this is everything of the form A comma B plus X comma 0 for all values of X. This is the set of all points A plus X, B plus 0, or B for all values of X. Now, if you look at A plus X for all values of X, this is exactly the same as all values of X, because every number X, every real number is of the form A plus X. This is a set of all X comma B, X and R. So in fact, if I take a point A comma B, the left coset is also this line. It's the horizontal line, y equals B. So here we have a very beautiful picture of an infinite quotient group. So we have the group G equal to R2, the subgroup H equal to the x-axis, all points of the form X comma 0, X and R, and the quotient group R2 mod H is the set of all horizontal lines, that is, lines parallel to the x-axis. That is, it's the set of all things of the form X comma B, X and R for all B. And how do you add two cosets? If you have the coset 0B1 plus H and 0B2 plus H, you just add these representatives, you get 0B1 plus B2 plus H. So we've just defined addition of horizontal lines. This line plus this line is the line B1 plus B2. Okay. So there's an interesting little bit of geometry embedded in this notion of quotient group. Let's look at some more examples. So let's remember that, let's say that, so gamma n, which is my notation for now for the cyclic group of order n, this is a group with n elements, a squared, a cubed, the powers of a up to a to the n minus first, with the relation that a to the nth power is equal to e. And then a to the I times a to the j is defined to be a to the I plus j. But of course, so this is how you define multiplication in the cyclic group. But if I plus j is bigger than n, you can just reduce it because a to the n is equal to the identity. So let's see if we can prove something about quotients of cyclic groups. Let's start by considering subgroups of finite cyclic groups. So let G be the cyclic group of order n, and let H be a subgroup of G, a subgroup of gamma n. So first of all, we know that E, which is a to the 0, is in H, because every subgroup of a group must contain the identity. Suppose I let D be the, so let's just say the two cases. So case 1, H is just equal to the identity. So that's a simple case. And case 2 is H is not the identity. So there exists some element a to the I in H where I is at least 1, right? Because the group only contains powers of A from 0 up to n minus 1. And if there's something other than E, then it has some positive power of A. So let D be the smallest integer, positive integer, such that a to the d is in H. That is, it's a finite set of powers of A, and take the smallest power of A that's in the subgroup H. So I claim that D, in fact, divides the order of the group N. Why is that? Well, by just doing long division, by the division algorithm, if you divide N by D, you get a quotient Q and a remainder R, where the remainder is between 0 and D minus 1. Now, if you take a to the n, that's the identity. This is a cyclic group of order n. A to the n is the identity. But n I've written as dq plus r. That's a to the dq times a to the r. Or that's a to the d to the q times a to the r. And of course, because a to the d is in the group, a to the d to any power is also in the group, because the group is closed under multiplication. So a to the r is a to the dq inverse, right? This times this is the identity. A to the r is a to the dq inverse. This is in the subgroup H, because H is closed under taking powers and taking inverses. But R is smaller than D. So R less than or equal to D minus 1 implies R is not positive, because D was the smallest positive power of A that was in H. So R can't be positive, so R has to be 0. So N is equal to D times Q. So this D divides N. And so every element of the subgroup H is a power of D. So H is the identity, A to the D, A to the 2D, A to the 3D. Just keep taking powers of D, A to the Q minus 1D. The next higher power would be A to the QD, but A to the QD is A to the N is E. So this is cyclic, it comes back on itself. So H, the subgroup H, is just the powers of D, and there are how many powers of D? 0 times D, 1 times D, up to Q minus 1 times D, there are Q of them. So the order of H is Q. So every subgroup of the cyclic group of order N is a cyclic group itself generated by an element A to the D, where D divides N, and the order of the subgroup, every subgroup H, and the order of H is N over D, which is some number, whatever it is, Q. So this describes all subgroups of a cyclic group. So for example, suppose we take the cyclic group of order 15. This contains 15 elements, A squared, A cubed, up to A to the 14th, and A to the 15th is the identity. What are the divisors of 15? 1, 3, 5, and 15. So gamma 15 contains exactly 4 subgroups. For example, suppose we take the divisor D equal to 5. So we have a subgroup, I'll call it H5, which consists of the powers of A to the 5th, E, A to the 5th, A to the 10th, and that's it, because A to the 15th is the identity. So this is the subgroup generated by A to the 5th, and the order of H5 is 15 over 3, which is 5. So this subgroup generated by the powers of A to the 5th has order 3, and they're going to be 5 left cosets. Let's try to calculate them. So we have gamma 15 consisting of E, A squared, up to A to the 14th, where A to the 15th is the identity. We take the subgroup generated by A to the 5th, which is E, A to the 5th, A to the 10th. So the order of H is 3. If we look at the left cosets, gamma 15 mod H, the number of elements in this is the order of gamma 15 over the order of h, which is 15 over 3, which is 5. This is just by Lagrange's theorem, right? The number of cosets of a group is the order of the group divided by the order of the subgroup. And what are the left cosets? So we have E times H is H. A times H is A times A to the 5th, A to the 10th. You multiply everything in the subgroup by A, you get A to the 6th, A to the 11th. A squared times H, you multiply everything in the subgroup by A squared, you get A squared, A to the 7th, A to the 12th. A cubed times H, you multiply everything by A cubed, you get A cubed, A to the 8th, A to the 13th. A to the 4th times H, you get A to the 4th, A to the 9th, A to the 14th. And you look, here we have 5 different cosets. They're pairwise disjoint. Every element of the group belongs to one and only one of these cosets. So these are the 5 left cosets. These together constitute gamma 15 mod H. This quotient group consists of 5 cosets. There are 5 elements in the quotient group. Each element itself is a subset of the group with 3 elements in it. But these are the 5 elements of the quotient group. If you took something else, let's say A to the 11th times H, what would that be? That would be A to the 11th times E, A to the 5th, A to the 10th. That's A to the 11th, A to the 16th, A to the 21st. That's A to the 11th, A to the 16th, A to the 15th is E, so that's the same as A. A to the 21st is the same as A to the 6th. That's exactly this set. This is AH. We know there cannot be a 6th coset. So the coset A to the 11th H has to be one of these, and it turns out to be exactly this guy. So I think really to understand what's going on, you have to do calculations like this by yourself and follow in the notes or look at the lecture again to understand what's going on. Okay. Any questions? Now, there is an important connection between normal subgroups and group homomorphisms. So let's recall the definition of a homomorphism. So let G and G prime be groups of function f from G to G prime is a homomorphism if it satisfies the following property. If I take f of xy, that's equal to f of x times f of y for all elements x and y in the group. And notice x and y are in the group, so this is multiplication in G. F of x and f of y are in G prime. So this is multiplication in G prime. And if either of these groups were additive, you would write this additively. So what's an example? Suppose I take G to be the real numbers R with addition as the binary operation. And I take G prime to be R star. This means the non-zero real numbers with multiplication as the binary operation. And suppose I let f of x be the function e to the x. So what do we have on the left? The operation in this additive group is addition. This is f of x plus y. That's equal to e to the x plus y. But you learn in pre-calculus or somewhere, e to the x plus y is e to the x times e to the y. This is f of x times f of y. So the exponential function is a group homomorphism. That's just a very pretty example of something that you learned in calculus coming up in algebra. What's another example? Suppose we take a group G and an element X in G. Let's say an element A in G. So define f of x. So define a function f from the group to itself by f of x is equal to ax A inverse. This is called conjugation by A. But for every x, this is f of x. So what is f of x y? That's A x y A inverse. Of course, that's the same as ax times e times y times A inverse. Because you can always multiply by the identity. And the identity is the same as A inverse A, y A inverse. And if I group it like this, you can see this is exactly f of x, and this is exactly f of y. So conjugation by an element is a group homomorphism. suppose I take the function from R2, the plane, to R by f of a point xy is just equal to x. So this sends a vector in R2 to a number in R. F of xy equals x. What is the picture of that? Well, here's a picture. If this is the point xy, it's really projecting it down to, well, maybe I'll do it like this, R2 to R2. F of xy is x comma 0. So then any vector, wherever it is projected onto the x-axis. Right? This just takes a vector and you drop the perpendicular or raise the perpendicular to the x-axis, and that's the image of the point xy. Is this a homomorphism? So suppose I take 2 points x1, y1 and x2, y2. I add them and apply f to that. So that's f of x1 plus x2, y1 plus y2, f of that point. And when you project it onto the x-axis, that's equal to x1 plus x2. But x1 is f of x1 comma y1, and x2 is f of x2 comma y2. So this equals this. This is a homomorphism. So this sort of geometric projection of a vector onto the x-axis is a homomorphism. That's kind of interesting. What's the identity in this group? The identity in R2 is just the point 0, 0. You add 0, 0 to any vector, it doesn't change. So suppose we want to define what we'll call the kernel of this function f. This is all the points x, y in R2 such that f of xy is 0, 0. You want to find all the points that project onto 0. So this is all the points x, y in R2. What is f of xy? It's x comma 0. So all the points where x comma 0 is equal to 0 comma 0. And the only way that happens is if x is 0. So this is all the points x comma y where x is 0, or in other words, the set of all points 0, y for any y. What is that? That is the y-axis. So if you have the homomorphism of the plane of R2, which sends every point to its projection on the x-axis, the elements which get sent to the identity are the y-axis. So everything on the y-axis projects to 0, 0, and nothing else does. So again, we've mentioned this previously, but it's very important to go through these definitions again. Let me draw kind of a picture of this. Suppose we have a homomorphism from G to G prime. So here's G prime. Here we have the identity over in G prime. And if you look at everything in G that F sends to the identity in G prime, So the kernel of F is all elements X in G, such that F of X is the identity. Everything that gets mapped to G prime. Now, first of all, I claim that E is in the kernel of F. That is, F of E, E is the identity in G. The identity always gets mapped to the identity. Why is that? Well, we can use the following proof of this claim. E times E is equal to E, or E is equal to E times E. So F of E is F of E times E. And because F is a homomorphism, this is F of E times F of E. This is from the definition of a homomorphism. So multiply this equation by F of E inverse. You have, on the one hand, F of E equals F of E, F of E. You multiply by F of E inverse. F of E inverse times F of E, that's the identity in E prime. F of E inverse times F of E, that's the identity in E prime again. E prime times F of E, this is the identity, so this is F of E. So F of E equals E prime. That's a proof. And the beautiful fact about that connects homomorphisms and normal subgroups is the following. Suppose you have a homomorphism from G to G prime. The kernel of F, which is all elements of G, such that F of E equals E prime, is a normal subgroup of G. So when I have G, G prime, E, and over here, I have the kernel, everything gets mapped to that single element. This kernel is a normal subgroup of G prime. So proof. First of all, F of E equals E prime. I just proved that. So E is in the kernel of F. So the kernel of F does contain the identity. And if X and Y are in the kernel of F, then F of X equals the identity, and F of Y equals the identity, which means F of X times Y, which is F of X times F of Y, is E prime times E prime, is E prime. So XY is in the kernel. So the kernel is also closed under multiplication. And if F of X, if X is in the kernel, then F of X is equal to E prime. We know that E is equal to X times X inverse. That implies that F of E is F of X, X inverse, is f of x times f of x inverse, but f of x is the identity. This is e prime times f of x inverse, which is f of x inverse. And f of e is the identity also. So if you just track through this equation, f of x inverse equals e, so x inverse is in the kernel. So the kernel of f satisfies the three requirements to be a subgroup. It contains the identity. If two elements are in the kernel, so is the product. And if every element in the kernel also has its inverse in the kernel. So therefore, kernel of f is a subgroup of G. Let's prove kernel of f is a normal subgroup. So let x be in the kernel of f, let A be in the group. What is f of ax A inverse? That's f of A, f of x, f of A inverse. But f of x is the identity because it's in the kernel. So this is f of A e times f of A inverse, this is the identity. This is just f of A times f of A inverse, which is f of A times A inverse, which is f of e, which is e prime. So if x is in the kernel of f, then ax A inverse is in the kernel of f. So A times the kernel of f times A inverse is contained in the kernel of f for elements of the group. So therefore, kernel of f is a normal subgroup. So this establishes a connection between homomorphisms and normal subgroups. Whenever you have a homomorphism, the kernel is a normal subgroup. And in fact, the opposite is true. So this says the kernel of a homomorphism is a normal subgroup. And what would the opposite of that statement be, or the converse? It would be that every normal subgroup is the kernel of a homomorphism. So let N be a normal subgroup of G. So we have the group G and we have the quotient group. And define a function, I'll call it pi, from G to G mod N by pi of X is the left coset Xn. So this sends every element of the group to a coset. And I claim this is a homomorphism. So for all x and y in G, pi of x times y is xyn. It's that left coset, which is the product of xn and yn, which is pi of x times pi of y. So this function is a homomorphism. And what is the kernel of pi? It's all elements x and g such that pi of x is equal to the identity. The identity is n, g mod n. So this is all x and g. What is pi of x? xn equals n. And the only cosets of n which are equal to n are n. So that's what I wanted to show. If you have a normal subgroup and you take the quotient group and you look at this function that sends x to the coset xn, this is a homomorphism. And the kernel is just the set of elements in n, it's n. So every normal subgroup is n is the kernel of this particular homomorphism. So we have now a kind of a one-to-one correspondence between homomorphisms and normal subgroups. And we're actually going to spend probably the rest of the semester just trying to understand these connections between groups, subgroups, normal subgroups, and homomorphisms. Okay. All right, well, we went through a lot today. There's also a homework assignment I posted, homework 8, I think. And I think basically, again, all the homeworks we have for the rest of the term are going to be on groups and subgroups and homomorphisms. So you really need to devote a lot of time to trying to understand these concepts. Okay. Questions about this? This is a lot of material to absorb. Okay, well, if not, I guess, then we're done for the day. If you have questions and you want to set up just on a Zoom session online to ask me a few questions, you can always, as I keep saying, send me an email and we'll set up a time that works, either for you individually or for a group of students together, whatever is convenient. Okay. Then looks like a lovely day, so enjoy the day. Be back on Wednesday. Bye all.